I'm going to pick up from where we left off last time. I'll do a little review, but this is, I guess, the second day of, or, we didn't really get very far last time, but the second day of recommendation systems from going from predictions to decisions, right? So in the first day, we mostly covered how do you predict what someone's, what rating someone is going to give, or what behavior that maps to whatever 0 or 1 that someone's going to give. And then last time we started talking about all the various ways, last time I mean last Wednesday, we started talking about all the various ways that might not go very well. And then sort of this time we're going to continue picking up that and specifically talk about capacity constraints. But before that, if my clicker works. Sometimes it works, sometimes it doesn't. Okay, before that, a few quick announcements. So again, because of a variety of scheduling reasons, there's another guest lecture on Monday. This is going to be in person. We'll do the same thing that we did for Drupal, in that we're going to potentially record. We are going to record it. It's going to be on Canvas, but then I'm going to remove it from Canvas. We're not going to post online. I'm really excited about this. It's Neil Parikh. He is he's the director of AI under the Chief Technology Office for the City of New York. He has like a really rich background in sort of, both in he sort of came up technically, so he has a PhD in machine learning or machine learning related things, but then he sort of went into like the startup world and also in government. So really a broad mix of experiences in really applying data science and machine learning tools in like really hard real world settings. So I think that's going to be a really great conversation. Please show up with your questions. Okay. Next announcement, we're going to add office hours for me. They're definitely always going to be the week before homeworks are due. I'll also add them with demand, but like we're just going to make them ad hoc in the announcements. But they're whenever they happen, they're going to happen Fridays, 1:30 to 2:30. So right before Ja's office hours, which are 2:30 to. Did I get that wrong? Are mine 12:30 to 1:30, and then his are 1:30 to 2:30? I got that wrong. Okay, yeah. So wherever his are, mine's the 1 hour before that. So yeah, so this is wrong, but yeah, so mine will be 12:30 to 1:30, and it'll also be on Zoom, just because it's right before his, so you don't have to like go from physical to Zoom. It will be a different Zoom link. And then homework 2 is due Tuesday. There's going to be a quiz next week as well. Are there any questions about logistics? There were a few questions on @STEM about like the homework grading, because like the median was technically above 100%. I'll talk about that in a little bit. Like I guess long story short, like don't worry about that. Like if for the homework grades, like 100% is whatever 16, it's fine if the median is higher than that. Like you're not gonna like get a bad grade in the class because other people did the bonuses. To the the homeworks are really meant to just like make sure people are understanding things, and like homeworks and quizzes are really just meant as make sure that you're keeping up in the class, getting to implement things, really understanding things. Like they're like homeworks and quizzes, like unless you don't do them or like do poorly on them, are not going to be the differentiator for grades. They should be, yes. Yeah, homework grades should be posted. I don't know if they've been pushed to Canvas yet. They're definitely on Gradescope. Any questions about that? Okay, cool. So I guess before we actually get started, I just wanted to do a histogram. I mean, I removed a few outliers, but a histogram of the final estimate people gave for homework 1, which is like after y'all ran through many estimates of what the balance can be between Clinton and Trump based on sort of the same data, again removing a few outliers. y'all's estimates really ranged everywhere from like really 0.48 to 0.54. And the purpose I have this here is that sort of, I think this is undercovered in a lot of like when we're analyzing just like existing data collection or like especially interpreting polls, is that everyone in the class had the same exact data set, sort of sat through the same lectures on how to analyze things, basically did an entire homework where we instructed you to like do the same exact thing. And then the sort of the estimates ranged from which like in a polling context, like in a binary election where like one of them is going to win, it ranged from 0.48 to 0.54, which is like, you know, a close election to like one person is definitely going to win, right? It has an 8-point lead in the 2% vote margin. And so this is sort of very similar to, I think I put this at the suggested readings in one of the lectures, is this is something, so the New York Times actually ran this exercise as well, where they gave actually the same data I gave y'all to 4 different pollsters, and then sort of had them also sort of do basically the same, like, you know, come up with their best estimate. And they basically found the exact same thing where sort of, I think one group said that it was around, sort of gave Trump +1, so around 0.4849 for Clinton, and then a bunch of the other groups were around 0.52, 0.53 for Clinton. So yeah, I thought that was interesting that y'all basically replicated that with the same data set. Oh, so the question is like, what data did I give you? So the pollster data, sort of, so DF poll was like literally the poll, like a single poll that some survey company ran in Florida for the 2016 election, I think a few weeks or the month before the election. And so that was, I mean, I removed, it wasn't exactly the data set, like in the sense that like I like renamed some of the things. So for example, like the polling data set had like age categories that were slightly different than the demographic data set. And so like I just like renamed them to make sure they were the same. And like I did a few things like that to make like y'all's lives easier to like combine the two. But yeah, so like, but the actual like the response, and then I removed a few responses and things like that. But the actual responses were, yeah, from that poll that someone actually ran for the 2016 election. The DF demographics were like some estimates of the population distribution, like the joint estimate. I actually got that from sort of someone else, actually one of the pollsters who responded. So I mean, who like were in that New York Times article. Sort of I know them, so I just like emailed them and asked them for like their estimates that they used for the population distribution. Yeah, so the question is so yeah, so I mean, if you have this like mismatch of ranges where like, you know, one data set has like, you know, for example, I think like 18 to 34, and the other one had like 18 to 25, and then a separate 25 to 34, things like that. Like what could you do? Yeah, I mean, you sort of, you have to make the assumptions at some point of like what your population distribution is. And so there's a variety of ways you can do that. Like you can try to sort of like, you can assume that the age is uniform, and that it's just like those are just like sample ages for people, or you can like try to do something smarter where you can sort of either do that multiple times, or you can say that they're like some combination of like the two different brackets. Yeah, so I mean, but I do think that there's like a broader lesson here where Oftentimes in data science, you're going to run into this where it's convenient to discretize into like coarser buckets. I always forget which way coarse means. Into less fine buckets, and to sort of like, go from like age, which is like an integer, to like buckets that are like 18 to 25 or something. It's often useful to do that as late in the as late as possible in your pipeline, exactly for issues like this. Like you don't like it might be convenient to do it for some reasons, but then like downstream it could have like annoying implications, and so just like do that as late as possible. Any other questions here? Okay. Okay, so let's move on to recommendation systems, and in particular, the first thing that we're going to talk about is dealing with capacity constraints. So this is trying to pick up where we left last time, but I'll do a bit of a recap. So what are we going to do here first? And what we talked about last time is like, why is capacity constraints like an issue? Like what goes wrong if you just do recommendations without like thinking about capacity constraints? Then we're going to do sort of a detour that is going to be related, but slight detour that's solving an easier problem instead of solving the actual problem that we have in recommendations. And then we're going to use insights from that easier problem to like what you can do in practice. Okay, so just as another motivating example, I'm basically going to give away the plot that you should observe in your homework, where in the homework we ask you to sort of first use the naive method of recommending, for each person, just get the item with the highest prediction and then recommend that single item, or yeah, recommend that item for that user. And then if you do that, you're going to observe a plot like this, sort of observe that the y-axis is on the log scale. And so like this is 10 times more than this, is 100 times more than that, and so on. And so you'll observe something that like 1,000, so about half the items were never recommended. So I think this is with recommending just like a one item to each user. In the homework, we might have asked you to do 10 items per. I forget what we asked you to do for the histogram. So this might not be exactly what you observe. But if you do one item for each person, then you observe that about half the items were never recommended, and that like one item was recommended about 300 times, right? So that there's a huge skew in sort of how often different items were recommended if you just do the naive prediction. And like maybe this is a good thing, right? Like maybe half the items are actually crap and no one likes them, and like one item is like everyone likes. And in a setting like movies where there's like zero marginal cost of just like creating copies and distributing whatever, like this might be a good thing. But in settings where you're selling or where you're like selling clothes or something, and you have only 10 copies of sort of the item that's been recommended 300 times, then this might be a problem. Okay, so what's the challenge? In many settings, you are recommending items with capacity constraints. I don't want to repeat the examples. If you ignore them, then bad things happen. And so then the question is, how should you factor in capacity in your recommendations? Any questions about the high-level motivation? Okay, so let's slightly formalize this, just to add a little bit of notation to make our lives easier. There's not going to be too much notation. There's not going to be like equations here like there was in the polling setting. Okay, so let's just say you have some number of items and some number of users, but for simplicity, let's just say that we only have one copy of each item, right? And actually, I think here I did different number of users and items. I think for the simplicity, I'm even going to assume that you have the same number of users and items for like the simple problem. And then you want to recommend one item to each user. So users are indexed by I, items are indexed by j. And so j of I is a function that maps sort of for the user I, what item are they recommended. And again, for simplicity, let's just assume that each user is just like going to consume the item that you recommend. That you're not like recommending, you're actually like forcing them to buy it. Right? Again, that's not reality, but for now, let's just assume that that's going to happen. In the next section on pricing, we're going to get into sort of relaxing, sort of like trying to formally think about what happens when that's not true, right? When, like, for example, the price of an object affects the probability that they end up buying it. And then, like, how do you reason about prices then? But for now, we're just going to assume that, like, the user is going to consume the item that you recommended to them. And this is an assumption that might not be true, but for now, we're going to assume that the objective is to maximize the sum of the predicted ratings of consumed items, right? So what that means is for each user I, the rating, like I have some predicted rating ij for each item j, and I just want to maximize the sum of those ratings for the actual item that I recommended to them. So this is similar to what I had last. Okay, and so, but however, we have the constraint that each item can only be recommended once, right? So if we didn't have this constraint that each item can only be recommended once, then we would do what the naive method we did last time, right? For each item, for each user, just pick the highest predicted item, and that would maximize this sum if you do that for each user, right? Are there any questions about? I'll pause here. Yeah. So the question is like, are the rating, like what are these ratings Rij? So they can be between 0 and 1. They can just be whatever that your prediction spat out. So in the first lecture in recommendations, we talked about filling in that matrix, right? Of what the predictions that that user I likes for item j. And so whatever that prediction is, whatever the range is, like I'm just going to assume that I have that filled in matrix. And then this is how I'm going to use it. Any other questions about the setup? Okay, so I want to maximize the sum of the predicted ratings. And if I didn't have this constraint of only being recommended once, then I would just do what I talked about last time, which is the naive method. So now the question is, okay, what should we do if we have this additional constraint? And this is just mathematically what that means, but so this is just saying that the item that person I is recommended is not the same as the item that person I prime is recommended. Okay. So it turns out that some of you might have learned this in an undergrad algorithms class, but it's completely fine if you don't, because there's a Python function to do this. But it turns out that the problem that I said in the previous slide is actually known as something called maximum weight matching, which sort of what that means is I draw a graph of users on one side and items on the other. So this is just a way to visualize the matrix, right? So I filled in that matrix, and this is a different way to visualize that matrix, where I'm drawing a bipartite graph. Bipartite meaning there's a bunch of people on one side, a bunch of items on the other side, and edges are only from one side to the other. There's no edges between people on the same side. But yeah, so we draw a bipartite graph of users and items, and then we draw a bunch of edges between each user and each item, which is what the predicted rating is, right? So this means that we predict that user 1 rates item 1 and 11. User 1 rates item 4 and also an 11. User 4 rates item 3 a 3, and so on, right? So this is just a visualization of the matrix. And then what maximum weight matching says is I want to find a matching. So a matching is something where each side has exactly one edge to the other side. So each side, so each sort of each user is being matched or assigned exactly one item on the other side. And so that's a matching. And then I want to find the maximum weight matching. By maximum weight is exactly the problem on the previous slide. That I want to find the matching such that you maximize the sum of the edge weights in your matching. So this is just sort of, I didn't say anything new here. This is just an algorithmic transformation. I mean, this is just a notational transformation of what I had said on the previous slide. But it turns out this view of the world is really nice because there's a lot of algorithms to solve maximum weight matching and a whole bunch of variations to solve it optimally. And so it turns out there's even a nice SciPy function to solve maximum weight matching as I described it. And so this ends up being the solution, and I'll dig into this in the next slide, but this ends up being the solution to the maximum weight matching described by this matrix. Any questions here? I know not all of you are going to go down maybe an algorithmic track, but I do want to sort of at a high level say that this ends up being a very useful transformation in general, where to think about matrices and graphs as matrices. Like sort of that connection unlocks a lot of algorithms and a lot of intuition if you're ever in a setting where you're thinking about graphs and matrices a lot. So yeah, I just want to point out that this is a very common thing that's done. So yeah, so the question is does it have to be a bipartite graph to be expressed as a matrix? No. So in general, you can have okay. So sorry, the specific transformation that I did here was all the users are rows and all the items are columns, right? And then the number in the cell is the edge weight, right? And so for that specific transformation, yes, that can only be used for a bipartite graph. In general, what you do is the common view is every node in your graph is both a row and a column in your matrix. And then all of the cells are just what the edge weights are between that pair of nodes. And so the diagonal would be self edge weights, what's your edge to yourself. And then the off diagonals are what's your edges to other others. And then once you have that matrix, it turns out that looking at the eigenvalues of that matrix or the eigenvalues of a slight transformation of that matrix actually tells you a lot of graph properties. Okay, sorry, that was an aside. But for now, I just want to tell you about the transformation because for example, that's a nice way to view this problem, and then you can use SciPy functions. Okay, but what are some actual insights from this? So I don't want to talk about the algorithm to actually solve maximum weight matching. For now, let's just treat it as a black box. But what I do want to talk about is, for this example, we solved it. And then what are some insights that we can use that tell us how to do recommendations in practice with capacity constraints, right? So what are some observations that we have when we go from here to here? So I think the first one, which might be obvious, but maybe not, is some users are not going to be matched with their most preferred item, right? So user 1 rates item 1 an 11 and item 2 a 10, but got matched with item 2 instead. Similarly, some items are not going to be matched with the user that likes it the most, right? So Item 4, again, user 1 thought it was an 11, user 4 thought it was a 7, but item 4 ended up with user 4. Right, so it's on both sides, you can end up with like second or third preferences. However, so like what are the reasons that someone might get their second choice or their third choice is if a user likes multiple items similarly, then that might be why they get their second choice, right? So like user 1 ends up liking basically items 1, 2, and 4 as an 11, a 10, and an 11. And the only one they really dislike is item 3, which is a 2. And so there's not a lot of loss in my objective function to go from an 11 to a 10, right? That's a loss of 1, like 10%. And so I don't mind doing that. And so in this case, the maximum weight matching sort of used the flexibility in user 1 to like maximize maybe another user who might be less flexible. However, if only one user likes some item, then you should make sure that the item and user are matched. Right. So these are just some like qualitative insights out of the solution, and we're going to come back to this when talking about how to like do approximations for the maximum weight matching. Are there any questions here? Okay. So why am I even talking about approximations? I told you a formulation of a problem, and then I told you how to solve it exactly, and then I claimed that there was like a semi-efficient algorithm that I'm not going to explain to solve that problem, right? So like if that's all true, then why do I even need to talk about approximations? Why not just do this in reality? So there's a lot of issues with that simple formulation. The first one is everyone doesn't show up at once, right? To draw that graph, I needed to have users 1, 2, 3, and 4 all be there at the same time, or at least user 4 to show up before I have to give recommendations to user 1. In reality, that's not going to happen. Some users are going to come in tomorrow after I've already given recommendations to user 1. And in particular, I don't know which users are coming in tomorrow, right? I don't know what their preferences are. I don't know what their demographics are. I just don't know who I'm going to need to do recommendations for tomorrow. And so if I ignore them, then maybe I like give away an item today that the user who came in tomorrow would have like absolutely loved, and that's the only thing they would have loved, right? Then you lost a potential sale, you lost a potential happy user if you didn't leave items for them. Okay. The second one, which again, really we're going to get into starting next Wednesday, so after the guest lecture, which is on pricing, which is you can't match people, you can only recommend them items, right? So even if I solve that maximum weight matching exactly and then like give people the recommendations as a result, I'm not actually going to get like the utility that sort of that result predicted, because some people might not consume the item that you recommended to them. And so like, let's say you recommend someone and like, right, like let's say you have a super high value item that everyone likes and you recommend it to one person and that person doesn't end up consuming it. Then you ended up wasting that, you ended up wasting that recommendation. And I think this is, okay, so I think the next one is something that's often forgotten, especially in like an sort of like an optimization view of the world where like constraints are like hard constraints, is like constraints are never hard, right? Sort of your capacity constraints are also soft in the sense that new items can be shipped to your warehouse all the time, and you can make that decision to like purchase and ship new items. You can also spend more money to expedite shipments, for example. And so oftentimes it might be, and again, for those of you who have an optimization background, this is exactly what sort of the dual variables tell you, right? Is what, like, how much do I gain in my objective if I soften my constraints a little bit? And in reality, that's sort of you're going to want to do that, or sometimes want to soften your constraints, and the maximum weight matching view of the world ignores that. Yeah, so I'll give an example where, okay, so the general view is that like the timescales might not match up, right? Like someone might show up 10 minutes from now, but you're not going to be able to buy another item for like a week, right? So that's that. But so I'll give a specific example, and I'm really going to dive into this in the pricing section when we talk about like dynamic pricing. But like let's take ride hailing and like how Uber and Lyft have to match drivers to riders. So and you know they do this all the time. So they're not recommending; they actually are matching, right? So they don't have to worry about this like potential lack of consumption. But let's say that we have like two drivers, or where like, and we have like one consumer right now, and both drivers are like 1 mile away from me, right? So in that sense, it doesn't matter which driver they match me with because they're going to arrive at approximately the same time. Oh, sorry. The unspoken assumption here is Uber wants to minimize like wait times for the customers, also wants to minimize like wasted time for the drivers, right? It wants to minimize the amount of time they're driving without a customer in their car. And so if they have two drivers like in different parts of the city, but both of them are a mile away from me, for me, it doesn't matter which one they match me with. But like if a customer has like opened the app and is like 10 feet away from one of the drivers, but hasn't pressed request yet, then they probably want to take some chance that like if that customer press requests in the next 30 seconds or something, that they would rather have that driver like available for the customer they're right next to, right? So it's in some sense it's a risk, but in expectation it'll probably like pay out. And so that's yeah. So like real world matching problems, especially in these like really like spatially distributed, like really fast settings, is like a fast, like, you know, there's like tens of PhDs working on this for many years to like, you know, optimize that last bit. Yeah, so the question is do companies in practice leverage data on the customers for like which customers get the most preferred items? I think they have to be very careful about that, right? So like what you don't want to, what you want to be careful about is like, are you like prioritizing a customer for a good reason versus a bad reason, right? Like sort of, are you prioritizing customers because they're a VIP customer who like pays a lot and you promised them that you would prioritize them? Or are you like prioritizing them because like they're like the squeaky, what's that phrase? The squeaky wheel gets the grease, right? Like they tend to complain, and like that's why, right? Like that could have negative downstream consequences for all sorts like equity, all sorts of reasons, if that's why you're prioritizing. And so in practice, I think companies are really, or they should be careful. Not all of them are, but like you should be careful about it's like Amy talked about on Monday, right? Is like, what are the like the second order effects of your objective function when you just like, you know, for example, if you're just matching to maximize like return customers, you might inadvertently be sort of prioritizing customers who like to complain. Yeah, so the question is like what's the generalization of like using max weight matching for either recommending multiple items to the same user, or recommending, you know, you have 5 of each item and you want to recommend the same item to 5 users. So we're going to ask you to do this in the homework, where sort of the night, like the way to do it so that it still works with the Python function is you can just like create multiple copies of like, so let's say it's not the problem you gave, but the other way around where you have 5 copies of the same item, right? So what you can do is you can just create like 5 copies of each item in like the matrix that you send in this Python function. So you can like duplicate item 1 to like item 1A, item 1B, so on, and sort of duplicate all the duplicate all of these edge weights that go into 1, and then create an item 2A, 2B, so on, duplicate all the edge weights, and then that's going to solve sort of solving that problem, and then you can map it into like, so then you can like once you have the solution, you can collapse them again. That's just like the stupid way to use the Python function, but like yeah, so like the formulations are equivalent. You can do the same thing on the user side. So okay, great question. So the question is in theory, if you sort of turn this into a free market and let people bid on each item, and then that drives up, and then like you float the prices and you like allow the prices to adjust such that the more people bid on an item, like the higher the prices and so on, and then like would that result in something that maximizes sort of maximum weight matching? That's a fascinating question that like has a lot of deep connections to econ theory. So like I'm happy to send these like keywords to look at next time. But like turns out there's something called and sort of like a Debreu equilibrium. Sort of you can talk about like arrow markets and so on. But like turns out doing something like that, creating a market like that maximizes not the sum of preferences, but it turns out it maximizes, properly formulated, it maximizes what's called the Nash welfare, which is the maximum of not the sum, but the sum of the item times the log of or maximizes the sum of the log of the ratings, weighted by budget constraints and blah, blah. But yeah, that's, so yeah, there's formulations to this, connections to econ theory about like what like a standard market does under many assumptions, blah, blah, blah. Any other questions? Okay. Okay, so yeah, so capacity constraints are soft. And then the last one is, or the last one I'm going to discuss, why you can't do this is, yes, this is like sort of, there exists semi-efficient algorithms, but when I say semi-efficient, I mean it in like the CS theory sense of the word, where it's polynomial in the number of users and items, but not like it's not exponential, and the runtime is not exponential, but it's polynomial, but it could still be like a bad polynomial that you don't want to run. But yeah, so there might be computational constraints and rerunning large-scale maximum weight matchings whenever a new user comes in. Oh, sorry, was that a question?
Shouldn't you, like I'm thinking from a business perspective, wouldn't it be better to give your best items to the users who want to come again to like buy future products and not give them their second or third one, if that might not encourage them to buy more stuff?
Yeah, so the question is wouldn't you like, okay, so I'll paraphrase the question, which is like the ratings that sort of like you might value some customers more, for example, like customers that are likely to repeat, and sort of, so you want to give them like their favorite thing, right? And I think that's a great point that sort of, okay, so my answer will be like far more general to this, which it's definitely true in practice that you like you don't want to maximize these like prediction things, right? Or like that's not ultimately what like the business objective is, right? The business objective is people spending the most money in the month. And so in that sense, you want to do recommendations that are going to causally sort of change whether someone's going to come back or not. And so if the dip for users where there's a big difference in whether they're going to come back, whether you give them the fourth favorite item or the first favorite item, you want to give them the first item. For users where that's not true, you want to maybe give them another item. So I'll give an example where there's not it's not exactly a recommendation setting, but let's say you're like a political campaign and you want like you have a limited number of advertising dollars or like ground game dollars and you want to see like which potential voters do I reach out to, right? Maybe reaching out to like someone who like already really supports your candidate is useless because like what you care about is you want to reach out to people who, because you reached out to them, voted for your candidate when they wouldn't have otherwise. And so in that sense, you like don't want to reach out to the people who die hard support you because like they're going to have voted otherwise, like for you, like no matter what you did. And you don't want to reach out to the people who really like don't support you, like really on the other side, because like no matter what you say to them, like they're not going to change their mind. And so you maybe want to be somewhere in like that mushy middle where your intervention has a causal impact on like the decisions people make. And so that sort of shows up here as well, right? Is you if you think about your intervention or your treatment as which item do I recommend them, then yes, you might want to recommend items that like sort of causally cause someone to come back or whatever your business objective is. But that's just in practice, that's just like doing these causal estimates, and we're going to talk about this later in the experimentation section and the causal inference section. Like that, what I just described is like the ideal view of the world of like how you make business decisions or just like any decisions ever. But like that's just extremely hard to do. Like it's extremely hard to get those estimates of what's going to cause someone to come back. Any other questions here? Okay, so what do you do in practice? And I'm going to sort of describe two solutions, and we're going to ask you to implement both of them in the homework. I think one of them is a bonus, the other one's not. But okay, so finding like the exact great solution requires a lot of like finding the right approximation to what I just said. Requires a lot of careful data science and modeling work in practice. Today, I'm just going to give like two high-level approaches. The exact implementation like very much depends on the context. Okay, so what are these two reasonable heuristics? The first one is what's called batching, which if you don't have to give recommendations immediately, then like wait for whatever 50 users to show up and then solve maximum weight matching for like those 50 users. And then the next 50 users show up, solve maximum weight matching for those 50 users, and so on, right? And ride-hailing marketplaces do something like this, or in theory could do something like this. I don't, using public knowledge, you can guess that they do something like this, which I don't want to break NDAs. So okay, so using public knowledge, you can assume that they do something like this, where so like that ride-hailing example that I gave before, right, is that you sort of there you can think about maximum weight matching as drivers are on one side, users are on the other, and the edge weights are like 1 over the distance, like the physical driving distance between the user and the driver, right? And so they can either, as soon as you press request, they can give you the closest driver to you, or as soon as they press request, there's like, the app spins for a little bit, and partially what they're doing when they're spinning is they're waiting to batch, you and like every other customer within a few miles that shows up in the next minute or something. And then they just solve some version of maximum weight matching for that batch of users, and then they move on. In practice, they do something far more complicated, but you could imagine that that's like one core part of the algorithm. So the benefits of that is you get some handling of capacity constraints and some handling of capacity constraints for future users, because you're like batching in this few minutes, and so you're like handling capacity constraints for every set of like 100 users or something. And so in some sense, you're like reserving items for customers who show up over the next minute, but you're not doing the long-term reservations, right? You're not like, if someone shows up 10 minutes later, or let's say you're in like a marketplace like Etsy, if someone shows up tomorrow, then you're not preserving capacity for the person who shows up tomorrow. In a ride-hailing context, that might be fine because quote-unquote items expire very quickly, right? Like, what is an item in the ride-hailing marketplace? It's a driver who is at a physical location at a physical point in time. And if they're like, if 10 minutes later, they're not there at that point in time, and you also don't want to waste 10 minutes. But like that, you can sense that that item has expired and there's a new copy of that driver who's a new item 10 minutes later. But in a context like Etsy, where items don't expire over like a day, that might not be a reasonable assumption. Any questions about batching? Yeah, so the question is there any ways to optimize that? And yeah, so I actually listened to a talk by someone from Lyft. So they told me I wasn't under NDA, so I can repeat everything from that talk. So I think this is also like in a public paper or something. But you could imagine optimizing the batch window, right? You can imagine sometimes batching within 10 seconds, sometimes batching between a minute, 2 minutes, 5 minutes, whatever, right? And why would you want to like sort of what's the trade? Whenever you think about optimization, you should always think about trade-offs, right? Like, what's the benefit of 30 seconds? What's the benefit of 5 minutes? The benefit of the harm of 5 minutes is someone who showed up at the beginning of that window has to wait 5 minutes for them to just be matched, right? Or let alone having someone drive to you. But on the other hand, if you just wait 30 seconds, then maybe that's like not enough batching, right? Maybe like that boils down to you just gave, like, obviously if you do like a millisecond window, then each person is their own batch. And so you've reduced it to the naive method, right? So you want to do a long enough batching window that sort of you get the benefits of this maximum matching. You want to do a short enough window that you piss off the people who showed up at the beginning. And what window size optimizes that is going to differ by time and place. And so you can think about like varying that batch window. Exactly. And you can empirically optimize that window, and you could do it, you can like change it for different settings, right? You can say, and like downtown and rush hour, a short enough batch window is nice because like a lot of customers showed up. And like other places, maybe you need a longer window. I'm not going to repeat the question, and I also worked at Uber for a period of time. I don't want to break NDAs. I'm happy to talk about this with you offline. But yeah, so I think the general answer is like in real life, people there's a combination of very good and very bad reasons to not do something, right? Like very good reasons can be I mean, just like developer time, like or like it's like complicated to engineer. But it could also be that there's other solutions that they found that were almost as effective. Then there's also just like very bad reasons that like no one thought of it, or like some manager was like, no, we're not doing this, or whatever. Yeah, that's a great question. So the question is how do you quantify trade-offs, right? So I gave like two like two different objectives that the batch window trades off in, right? Is that if you have a longer window, that sort of you're inconveniencing customers at the beginning. If you have a short window, you're sort of like inefficient overall. And so like that's now you have two objectives that you can think about as like there's like some fairness or equity or like tail, right? Like it's sort of you care about individuals, and then there's a second objective that you care like overall efficiency. And like these two objectives are on different scales. Like you can't just add them up and like have a master objective. And so I think that's a very good question, that how you compare objectives and how you weight them. And I think that just requires like and Amy talked about this on Monday a little bit, is that requires just like some conversation at the decision-making point of which of these objectives do you care about more. There's some data-driven ways to make that decision. So for example, if like both of these are like not your real objective, right? If your real objective is like revenue over a month, then there's some ways that you can try to measure how do these like intermediate objectives like differentially connect to your real objective. But yeah, that's a very hard thing to do. Any other questions here? Okay. And then the second one we're going to talk about, and this is what I'm going to talk about in detail, is you can create what are called index policies, which what I mean is, what by index policies I mean is just create a score for each item. So you have a user comes in. For that user, create a score for each item and just recommend the item or items with the highest score. That sounds a lot like the naive policy. And in some sense it is. So the goal is we want to create a score between each item j and each user I. So we want to create a score Sij. And then, yeah, pick the item with the maximum score, the argmax of the items for that user. And we've already seen an example, right? This is basically the naive method if the score is my rating, right? If I just say that the score between each item and each user is just the predicted rating, then that's an example of an index policy. But then we can generalize that thinking a little bit, right? There's no reason that the score between an item and a user is just their rating. You can factor in a lot of other things to the score, and you get all the benefits of maximizing by rating, right? You can do that immediately for each user. You don't have to think, you don't have to wait, you don't have to think about other users and so on. Yeah, so like why, like this is a very general class of policies. And like, why do you do this? Is they're efficient, right? So for, I just said this, for each user, you only have to consider their scores. You don't have to solve this like maximum weight matching problem that's polynomial in the number of users and the number of items. This is just what, like for each user, just calculate it for each item. You can explain these scores. If you care to explain these scores, you can explain them to users, right? You can say, I matched you or recommended you this item because you had a high predicted rating for it, or whatever else goes into my score function. Yeah, and so sort of this is related to the other two, is all information about other users is contained in how the score is constructed, right? So if I construct the score as just being my rating, then there's no information about other users that I'm using, right? I'm just using information about this user and this item. or this user and all the items. But in the example that I'll talk about next, you can incorporate information from other users into the score function without having to like wait for specific users to show up. Okay. Any questions about like the high level of like what an index policy is? Okay. So what matters in constructing an index policy? For this, I want to go back to, we solved the maximum weight matching and got some qualitative insights from like what matters there, right? Like what did an optimal solution look like? And so just to remind you what the goal is we want to construct an index policy that has all the benefits of like predicting by rating, which is like it's fast and like, you know, everything I just talked about, but it doesn't have the downsides of doing that, where the downsides being that you like ignored capacity constraints, right? So we want to construct a score function that takes into account all the qualitative insights we learned from maximum weight matching. So what are some of the things we learned? The higher the ratings by other users for an item, the lower my score should be, right? So in maximum weight matching, if a bunch of users similarly liked an item, then maybe you don't pick the top user for that item. Maybe you pick the second or third user because there's not that much loss, right? So, you know, yeah, so the higher ratings for other users, the smaller the score should be. The less capacity you have left for the item, the smaller the score should be, right? So if you have only like one of the item left, then, or if you have one of the item versus two of the item, then like sort of you should have a higher rating for them to actually be recommended. So the score should be smaller. And so here's an example of something that implements the two. And so I guess the third one that I didn't say because it's implicit is the higher my rating, my predicted rating for that item, the higher that score should be for me, right? So you still care about the individual user, but now you care about other users. And so here's an example. So you could have something, so I think I label what each of these things are. Okay, yeah, so let's just look at this by piece. So the first part is Rij. So you can, the first thing I care about is the higher my predicted rating is, the higher the score is going to be. The higher, so Rj bar is just the mean rating for that item across users. And so you can divide by the mean rating. And so this ratio is compared to the average user, how much do I like this item, right? If my rating is way above that of other users, then I want to recommend that more. What I didn't include here and didn't discuss, but you could also include is you can also normalize by the mean rating for that user, right? So if the same user likes basically everything, then like the score function should be lower. And so you could also divide by the mean rating for that user. Cj is the capacity, where the higher Cj is, the more the score should be. And then I have two parameters where I have some beta that's the power, sort of I take Cj to some power, so maybe like the square root or the cube root or something. And then I have some other parameter that I just tweak for the item. And then you could think about just like learning these parameters over time to like maximize some objective that you care about, right? You can learn these parameters to, for example, make sure, yeah, just sort of such that like the score function over time actually like is similar to what a maximum weight matching would get you, right? And so like, what are these parameters? Maybe parameter alpha j is like, this item should be over recommended for whatever reason, right? Like maybe like fewer people end up consuming it after it's recommended. And so you need to like learn over time that you need to over recommend that item. And then beta is the relative importance of capacity for the problem that you care about. So like if beta equals 0, then maybe like you just don't care about capacity constraints. If beta equals 1 or 2 or whatever, then you really care. So like I don't want to like emphasize this specific structure, like this formula is just something I made up. I want to emphasize that there's a lot of things you can do in a score function that replaces using just an average rating or using the rating for that item. And constructing a function like this gets all the benefits of using the predicted rating, but allows you to take into account other things that matters in your problem. And for those of you who for those of you who will go down maybe like a more CS algorithmic or theory route, index policies are like very special in CS theory in that you often try to like have a complicated algorithm that can be reduced. Like sort of a lot of seminal results in the field are saying we have this really complicated problem, we can approximate it or solve it exactly using an index algorithm, because index algorithms are like have all the benefits that I just talked about. And so like finding the right index policy for your setting is often like a really nice thing to do. Yeah, so if Sij was just exactly equal to Rij, this would be the naive approach. But now what I'm doing is I'm like adding some other things to the score, right? So for example, if one item has like a rating of a 5 from basically everyone, and another item has a rating of an average 1 from basically everyone, then for one item, you're going to be dividing by a 5, and another item, you're going to be dividing by a 1. And so like if user 1, if user I, so let's take j equals 1 and j equals 2, right? And for j equals 1, you're dividing by 5. For j equals 2, you're dividing by 1, right? Then the score function for item 1 is going to be for the same exact, like all the other variables, the score function for the first item is going to be 5 times less than the score function for the other item, right? And so if you're sorting and recommending the highest scored item for that user, you're going to recommend item 2 instead of item 1. Exactly. Yeah. So yeah, you could think about this division as looking at the relative rating, like a normalized rating for each item as opposed to the overall. And then these other things is like other things that matter, right? So capacity. So if you have two items that sort of the first part is all the same, but you have more of one item and less of the other item, then you should recommend the thing that you have more of. No, so yeah, so you should, I mean, what I'm going to talk about in a little bit is stable matching, where you have to consider from both perspectives. But yeah, for here, it's just like you just do this for each user. So for each user, you construct all their scores for each, so like I have one user, so I have Nikhil came to the website. Then for every user, I score all the items, and then I take the maximum item and recommend it to Nikhil. Exactly, right? So you can imagine you're learning these, so like alpha J and beta, you're like learning those parameters over like a long period of time. The capacity can be updated immediately, right? Like if I come to the website and I buy something, then the next user like is gonna like the capacity for that item goes down by 1. And so for the next user is gonna see a different score for the same exact item because of capacity. Yeah, so the question is can you incorporate the likelihood that someone's going to consume the product? Totally, you can and you should. Actually, in there's not a great framework to reason about that in the recommendation context without prices. or at least I don't think that is like a very clean way to do it. But like when we start doing pricing next Wednesday, that's actually going to be like a core like thing that we do, where for any given price, you reason about what is the probability that the customer buys it at that price. And there, it's just like a lot clean. Like you can do it in the recommendation context. It's just a lot cleaner to think about in the pricing context because you have like a clean objective function, which is like maximizing revenue. And so, and the probability that someone purchases something is like a very like core part. Like it's like it like immediately shows up in your objective of revenue. Yeah, so that's a great question. So what you can, so there's like, so in practice, sort of like in the Airbnb context, I think like another way to phrase that is like there's some more complicated function between the average rating and the capacity, right? So what's interesting about the Airbnb context is that there's like the same home, the same apartment is like simultaneously has like you have capacity 1, but you also have capacity 365, right? So you can, if you think about each item as being like this apartment on this day, then you have sort of 365 of like of an apartment, right? Because you can rent it each day of the year. If you think about as the capacity as being, or sorry, for the other way around. If you think about each item as being that apartment in one day, then you have capacity 1 for each item because like only one person can rent that apartment that day. But if you think about each item as being just that apartment, you have like 365 of that because there's like 365 opportunities in a year. And in practice, there's like, it's a mix of that because sort of, and we might, actually, no, we will talk about this, again, in the pricing context, is different items are substitutes and complements for each other, right? So, but by what I mean is, so like one day on Airbnb could be a substitute for another day, where if I, like, if instead of getting that Airbnb on Friday, if I can get it on Saturday instead, that might be almost as good. Yeah. Any other questions? Yeah. Okay. So yeah, so in the homework, we're going to ask you, I think we're going to give you a specific score function to construct. But yeah, so I mean, this is just like scratching the surface. As you can imagine, there's like a lot of like, it's going to be very application dependent what score function you end up constructing. Okay. Yeah, and so like, what are some like general lessons from like what we did here? And I think these are general lessons like when you're adapting algorithms for practice is if you first do the naive thing for each user, which is just take their highest predicted score, you might not be globally efficient, right? So like being naive might cost you when you like step back and think about all users. Even if you can't implement it, it's often useful to think about what the optimal solution would be for even a far like more simplified version of your problem, right? So like what we did here is we got intuition from maximum weight matching. Okay, so maximum weight matching did 2 functions here, right? Is 1, we could approximate it by batching, but 2, we could get intuition from it to know what matters in the score function, right? And I think that's a nice lesson, which you should try to think about what, before you think about practical constraints, think about what the optimal thing would be if you could ignore some of the practical constraints. And then index policies are a nice, very general way in many settings to decompose your problem and implement a practical solution. Okay, so I think we have 5 minutes left. I really want to start pricing on Wednesday, so I'm going to have slides for multi-sided preferences and just like give you the motivation here, but I don't think I'm going to cover this in class. So I'm just going to summarize. So in many modern online marketplaces, both sides have preferences, right? So in like a freelancing marketplace, a client might not want to work with a worker might not want to work for a specific client or do a specific type of job. Dating apps are, of course, like this. And so a match only happens if both sides like each other and have capacity and all of the other things. And so I'm not going to talk about, and so it turns out you can do something very similar to what we did, where in the earlier context, we talked about maximum weight matching and like got insights from that. Here you can sort of, it turns out there's a problem called stable marriage or stable matching, where you want to now match each side to the other side, taking into account preferences of the other side. And so what you do here is you get rank order preferences from each person. For each person, you get rank order preferences for the other side. So each student will rank all the universities that they want to go to. So this is actually used to match medical students to medical residencies, right? So each medical student in the US will submit a ranking over the residencies that they want to go to. And then the residents, there's some interviewing and stuff process, but then each residency will submit a ranking for each student that they interviewed. And then there's some centralized process to convert all of those rankings into a final matching. And then in the US, medical students like have to go to the residency that they got matched to. The residency has to sort of hire the student that they got matched to. And what you care about here, why this is different than maximum weight matching, is now you want like sort of the objective that people have done a lot of work on is you want matches to be stable. By what I mean is you don't want any pair, like let's say you don't want university A and student A to abandon the people that they each got matched to match with each other, right? So you don't want a situation where university A wants to abandon student C, student A wants to abandon university A to match with each other. And so that's called stability. And so then it turns out, and this is efficient to find, you can, again, for those of you with an algorithms background, there's like really nice algorithms to do this efficiently. And this is used essentially this exact thing, like not even an approximation, is used to match medical students to residencies. It's used to match students to high schools in a lot of major cities, including New York. And I mean, there's of course a lot of details in actually implementing this, but sort of what I wanted to get out of this, which I'll just let you read the slides, is there's again, you can't do this in like an online setting where like not everyone's showing up, right? All the reasons you can't implement maximum weight matching, you can't implement stable matching on a dating app, for example. But again, you can do approximations. So you can get lessons from stable matching and think about how to do score functions for every pair. And for those of you interested, I'll just let you read the slides. But I think that's all I had for today. Are there any questions? Oh, and then I guess the last thing that we, again, not get to is diversity and recommendation systems. We talked a little bit about it on Monday. There's some slides on it for those of you who want to read it.